Welcome to Live Overflow, and this is a beginner's tech video. So I have a very detailed walkthrough with a lot of explanations of very basic things for a level of protostar. So exploit exercises provides a variety of virtual machines to learn the basics of computer security, like vulnerability analysis, exploit development, debugging, and so forth. We will have a look at protostar. Protostar introduces the basic memory corruption issues, such as buffer overflows, format strings, and heap exploitation. Those are old school Linux exploitation things because they don't have any modern protection mechanisms such as ASLR or DEP. But they will be introduced in another virtual machine called Fusion. You can download it, you can download the image, and then you can just boot the virtual machine and log in as with user in the user account. The levels are in the folder of protostar bin, and in case you need root, you can log in as root with the password godmode. So protostar has some levels about stack exploitation, then format strings, some heap overflows, and then a few networking issues, and then we have final levels that kind of combine a few of those things. We will have a look at the first basic level, which is stack0. So let me quickly show you my setup. I have a VirtualBox where I run the protostar ISO. I have set up a host-only adapter for networking. In the preference, you can see you have to have a host-only network. You have to set up one here. So you can start this and boot it up, which I've already done, which is here. And you also have to look at the IP address that got assigned to the machine, because working in here is obviously possible, but it really sucks. So what I like to do is to use SSH to log into this machine. SSH should be installed, is installed on any Linux machine and also Mac, obviously. For Windows, if you're working on a Windows machine, have a look at a program called Putty, P-U-T-T-Y. So now we are logged in. I changed to bash because I like it more to have like this, the whole prefix here. So the levels are at op protostar bin. Oops, obviously I need to change the directory there. So our current working directory is protostar bin, and we can look at we can look at all the files here. With ls-la you can list all files, including hidden files. So here's our level stack0. Let's quickly just execute it and get a feeling for it. So it seems to wait for input. You type something in, press enter, and it says try again. Let's have a look at the source code. So we have a main function. We have two variables, modified and buffer. Modified is an integer, and buffer is a 64 character wide basic string. Modified is then set to 0, and then we do the get string. This was basically the input that was waiting here for me to typing something in, and the result will be stored in buffer. So the string I entered was stored in buffer. And then it's checked if modified is not 0. But if it's 0, it says try again. So this is what obviously should always happen. But if for some whatever magical reason it is not 0, you will get to you have changed the modified variable. If you are coming from a programming language like JavaScript, Python, Java, or something similar, you will think that nothing will ever happen. You will never reach this part. But C is a bit different because it's very low level and mistakes can happen. So let's have a look at gets. you should be, if you start to working on stuff like this, you should get familiar with the man pages of Linux. So with man and then the function or the program behind it, you get access to the Linux Programmer's Manual. And you can see here now the entry for gets. So it seems like gets is part of a family of functions that you can use to input, that you can use for input characters and strings. Our particular function wants a char pointer to somewhere. So this buffer is not a char, buffer is an array of chars, and so buffer is basically just a pointer, and a pointer is just an address pointing somewhere in memory. So the buffer itself is pointing to an area in memory where there's space for 64 characters. So and we can read it here. Reads a line from standard in into buffer, pointed by s. So it's writing it to the address that buffer points to, until either we terminate it with a new line. So basically, when I hit enter or enter file, and it's then replaced with a 0. So C doesn't really have strings. C only has arrays of single characters, and we define, or it's defined that the end of a string is null terminated. So if you have string handling functions, usually they will stop doing something once they reach the character 0, the null byte. And it also tells you here that there are no check for buffer overruns. See bugs below. And if you look below here, bugs, never use gets, because it is impossible to tell without knowing the data in advance how many characters gets will read. So if every time if a user can somehow modify how many characters will be inputted to gets, it will just continue to store characters past the end of the buffer supplied by S. And it's extremely dangerous to use. So never use gets, and if you see a program that is using gets, it's very likely to be exploitable, like in this case. So what else do we got here? Maybe explain standard in really quick. We have basically 3 mechanisms to communicate, 3 basic communication channels for a process. If we start the stack0 process, we have obviously a standard output. The standard output is for the program to give us, put out some characters or byte values or anything to output something. We have standard input, where we can put something into standard input and the program can read from it. And there's also standard error, which is used for debug or error purposes. Okay, not that important for this here now, but just so you don't get too confused too much. Next step is we should have a look at the disassembly of this code, and let's compare it to the real C code. As you may know, C code is compiled directly to assembler, and that assembler code is executed. So we will use the GNU debugger to have a look at this. GNU debugger of the file 0. You can also just start GDB like that and then load the file stack0 like this. Let's have a look at disassembly of the main function. As you can see, I don't like this kind of syntax. That is AT&T syntax. I like to set my disassembly flavor to Intel because I think that looks more sane. The difference between those two is a little bit, of course, what they use, AT&T uses the $sign a lot and the percentage sign. This doesn't happen with Intel language, and they are also reversed. So you see here the AND instruction, it has the constant first and then the register, while the Intel language has it the other way around. You have to read it like this. The move EBP is, you have a move, and then EBP And then the move is basically an assignment, EBP equals ESP. So ESP, the value of ESP is stored in EBP. For this AND instruction, the result will be always stored in the first register there. So ESP is ESP logical AND this constant here. Okay, so this is for me more natural to read. Like this is ESP and then this instruction with this. And here maybe the sub as well. So ESP minus 60 in hex, and that is all assigned to ESP again. So I think this is more natural than reading it the other way around. Let's set some breakpoints. The CPU will come from somewhere and will start executing the first instruction, and then just next instruction, just like this. Okay, and it will do the stuff that is listed here. So what we want to do is, first of all, let's break here to explain something about the stack. Then we want to break where do we want to break next? We want to break after the gets to see what's happening after the gets. And yeah, that's I think that's enough. So now we will restart the program, or run the program, and we will break at the first breakpoint, which is here at the ESP. So let's have a look at the registers. Registers are just like variables. You can think of them as variables and you have only a limited amount of them. Some of them have special purpose, which you will not use like directly or too much. You have like EAX, ECX, EDX, and EBX are more like general variables that you can use when you need them. ESP and EBP are used to work with the stack. So it's a stack pointer and the base pointer. And ASI and AD are ESI and EDI are used to often for function for like source and destination to have a little bit more meaning to it. And EIP is the instruction pointer telling you what will be the next instruction that will be executed. In this case, the next instruction will be the subtraction. And the other stuff is not that important right now. So we see that ESP is currently pointing at this address here. Let's examine X for examine 36 values on the stack by from the stack pointer on. So what's happening now here? It says it subtracts ESP 60. So ESP is currently pointing at this address, and what it does now is it makes space on the stack. So it moves the stack further up by subtracting it. The stack grows downwards. So by subtracting it, you get more values like before all of this. You get more space. So next instruction. And now we move this upwards. You can see here, this was the line previously, which was here. And now we subtracted zeros, hex 60, and now we have won all the space here. Then let's look. The next instruction is an assignment, a move again. And this is how variables work in assembler. So this is moving value 0 to this here. And you can already see in the source code that the modified variable is assigned 0. So this has probably something to do with the modified variable. We just made space on the stack, and this space is now used to work with these variables. Local variables like this will be handled on the stack. So it basically says us that the modified value is calculated by take the current stack pointer, add 5c to it, and this value resulting from this addition is the address, like the pointer. It points. It's an address that is pointing some. Or it's a value that is interpreted as an address, which is basically pointing somewhere, and at this address write 0. So what we can do is we can also examine the memory of this calculation now. So let's examine the memory of ESP. If you want to like output the values of interpret them as addresses and stuff, you need to add the $sign in GDB. So you can see currently modified is garbage that just was in memory beforehand, but it's pointing to this address here. So it's at 78C, and as you can see, this here on the stack is our modified variable. So if you remember, like this was the stack before we did stuff in the main function, and this one is just right before this. So we made place on the stack, now we have more space, and this value is the modified variable. And it's pretty safe to assume that part of this here are our 64 bytes for the buffer variable as well. That's why we have made so much space. Okay, so now we will do this assignment here. We will go one instruction further, and now we look again at the modified variable, and it's 0, so it got set to 0. Now let's let the program run again without us interfering. Continue. So now it's at the gets call, and it's waiting for our input. And now let's input something that is very easy recognizable. Let's input 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's include 40 A's. And now we have the breakpoint directly after the gets call. We can look at the disassembly main again. Now we are right here. And now let's have a look at our stack again. So we use the call that we had before, and as you can see, like this was our modified variable, and as you can see, here is where our input just landed. Those are all the A's. How do I know that this is A? I like to test. I always like to look at this with Python. Let's have Python up here because I think we have to do a few more conversions. So hex is 65. If you want to get the character of this value, you can use CHR. And if you ever wanted to know what the value from a character is, you can do the ORD of the character A, ORD, with 65. And if you want this to know what this is in hex, you can just get it in hex as well. Okay, so we can also have a look at the next instruction now, right? We are here, and we know that this here is our modified variable. And as you can see in the program code, after the gets, we do the if check. So now it gets the value from ESP plus 5C again, so this one, and moves it and saves it in EAX. And now it will make this look stupid. It tests EAX, and then it does a jump equals. This sounds stupid, like you would think, well, EAX is always like equal, but that's kind of not how it works. That's a very common test for if a value is 0. And if it's 0, it will, I think it will jump down here, and if it's like, wait, we can check that. We can check basically this should be the address of our string. So let's see. Yeah, you have changed. Okay, so if it's 0, we will jump will follow this jump down here, because this should be the try again. Yeah, and this points to you have changed a modified variable. Okay, so this is how our string looks like. Let's restart, let's rerun the tool again, and let's type in a few more characters. Let's add b, 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 b. So now we have 2 times b. Let's add 1 time for b's. And let's have a look at the stack. And as you can see, it just kept growing, just overwriting more and more. And you may already guess where this is going. If we can just like continue to add more characters here, we can overwrite more and more. And at one point, we can also overwrite the modified variable. So let's run this again. Oops. Continue. Code before, so we are right here now. Let's make 4 C's for this here. Okay, so if I now do continue, and now let's look at the stack, you see I just filled up everything just right before the modified variable. If you also count now how much we have input, how long our string is that we have put in there, you see it's just 64 bytes long. This is exactly how big our buffer was. So we shouldn't be able to write more. Also, but this is just partially true. Something that you don't see that happened here is that the string always terminates with a 0 byte. So in reality, the string is not this one. In reality, the string has a 0 byte at the end, and it's actually 65 bits long. We actually already have written a 0 byte into modified, but it's just 0, so we didn't notice it. Just keep that in mind. 64 doesn't mean that you can have 64 bytes like this. It will add a 0 byte at the end, and you have actually one more. But anyway, so if this is just how we got to the modified. If we add one more, character. First, let's continue this program, and it should say try again. Okay, let's restart. If we add one more character now, let's add a D. We should have written into here. We should have written a D into there. So let's see. Let's look at the stack, and it's true. Modified seems to be set to 44 now. Let's look at the disassembly code again, right? Now comes the comparison. So the next instruction moves the modified variable into EAX to test it. Let's have a look at the registers. We do a signal, we do next instruction, and we look at the registers. So we have moved the value of modified now into EAX, as you can see here. If you continue now, you have changed the modified variable. Isn't that crazy? So we can also test this now without GDB. Let's execute this again, and let's input one less than this. Should say try again, and it's with the D. You have changed the modified variable. Pretty cool. Okay, let's save this and kind of document it. I have created a folder protostar where we will save all those files. And cool. This is our first exploit, our first buffer overflow, where we have written past the space that we should have, and we have overwritten a value and redirected code flow, even though we thought that would never be possible. And I hope you have learned something.